I've collected some more magazine articles, and before the stack gets unmanageable, I thought I might do another video and see if there is still interest in this kind of thing. The first article is from the August 1959 issue of Electronics World called Shopping for a Hi-Fi Amplifier, and I'll talk about why I chose that one first in a minute. So here are the issues that I'm going to be talking about in this video. The first one is from Electronics World, and as I said, I'll tell you why that I did that one first. Then I'm going to be going back in time to Wireless World and look at some articles from 47 through 51. And one reason that I'm going to be doing that is I'm going to be using three articles, two sets of articles. First is the April-May 47 high-quality amplifier. This is the first discussion of the Williamson amplifier. I've talked about this before when I talked about hi-fi amplifiers or tube amplifiers for hi-fi, but I'm going to be using that as a model, and it's, in my mind, the most important article on hi-fi amplifiers, on tube amplifiers, because in it Williamson talks about a lot of things that we'll get to when we come back there. And then finally, the reason that I ended in November of 51 is the ultralinear amplifier. This was the attempt to finally get decent hi-fi out of the pentodes of the day. And once again, it is more or less the other end of the two bookends that I consider important from the early days of tube amplifiers, these two articles. So we'll be talking about the ultralinear a little bit also, but mainly what we'll be talking about there is why it was an improvement, but it didn't solve all the problems. So these are the articles we'll be talking about. So why did I start with this shopping for a hi-fi amplifier? Well, for one thing, this is written by one of my favorite authors, Norman Crowhurst. If you've seen some of my earlier videos, you know that I became enamored of his articles back in the 50s when I was still in high school. And this article is one of the best overviews of how you can relate the technical specifications of an amplifier to what you will hear in your living room. Now, of course, it's impossible really to do that, but he does talk about, in very practical terms, issues of frequency response, measuring distortion, and other things of that sort. And then he relates those to the listening experience, how you might look for various characteristics in an amplifier. But then, as he admits at the end of the article, the real proof is in the listening. The second article appeared in Wireless World in February of 1947, and this article actually predates the Williamson amplifier. So at the time this was written, and by the way, one of the author of this is one of the most prolific engineer authors of the period, P.J. Baxendall. The point of this article is trying to eliminate hum, particularly in the early stages of high-gain amplifiers. And as the subtitle indicates, reducing pickup in the first stage. One of the reasons that I like this particular article is it's not only very practical, but it also discusses trying to eliminate both electrostatic hum as well as electromagnetic hum. A lot of people are familiar with electrostatic hum, and they know that if you put a piece of metal around a circuit, that the metal will block to a large extent, electrostatic energy from coming inside the box. So if you do a good job of shielding, you can eliminate electrostatic hum, and most people are pretty good at that. The problem that most people have, or the reason that sometimes after all of their efforts to eliminate hum go unrewarded, they eventually stumble on electromagnetic hum. Now, electromagnetic hum is largely due to loops. Some people call them ground loops, but basically it is any loop in the, in this case, the first stage of an amplifier. And one of the reasons that that is important is that magnetic fields will pass through metal to some extent. Now, there are some metals, mu metal, for example, that will block or at least attenuate magnetic fields and other things like that. But in general, a thin piece of aluminum around a circuit will not block electromagnetic hum. And there is a lot of electromagnetic hum in an amplifier having a large power transformer. The magnetism from the transformer permeates pretty much everywhere. And the further the transformer is away from the input, the better. But the other thing you need to watch out for is how you locate the loops in the circuit. And I won't go into that in any more detail. Baxendale does a very good job in this article of explaining what that's all about. But it's an area that, frankly, baffled me for some time, and I finally wound up learning it many years after this article was written, and I wish I had seen this article before that. The next article is actually a pair of articles appearing in the April and May 47 issues, so just a few months after the one we just looked at, called Design for a High Quality Amplifier. And as you see here, this was written by Williamson and probably became the most famous amplifier design for tubes, at least through the 50s and 60s. But what I'm going to be doing here is more using this article as a staging ground for some of the other amplifier articles. And the theme of this entire video is going to be the development of good tube-based hi-fi amplifiers. This is the circuit of the Williamson amplifier. If you want more of an in-depth on this, you might want to look at the series I did on hi-fi tube amps. But I'm basically going to use this as a prop for what I consider to be the three issues that designers of tube amps had to solve. Williamson talks about all three of them in this article. The first is the output transformer, and this is the power transformer, by the way, and that's the rectifier. It's a little unusual to draw it this way, but this is the output transformer. And the design of an output transformer is, well, challenging. Generally, hi-fi tube amplifiers avoid single-ended because to do single-ended, you have to have a very large gap in the magnetic core of the transformer to eliminate saturation, or at least to reduce saturation. Because of that, single-ended amplifiers are incredibly inefficient. Almost exclusively, the better hi-fi amps of the day, tube amps, used a pair of tubes in push-pull, which meant a center-tapped transformer primary, and then a secondary, usually with multiple taps to adjust or to match the impedance of different kinds of speakers. But the design of that transformer, and Williamson talks about this a bit in his article, the number of windings. In other words, it's shown here, and most people think, well, that just means there's one winding that goes from here to here, and that's not true. Most hi-fi amplifiers of the day had anywhere from 3 to as many as 12 windings. In other words, there would be a winding like this and another one just like it, and the two were in parallel. And then there'd be a third, sometimes a fourth, fifth, sixth, seventh. The reason for that was to adjust the balance between inductance and capacitance. Now, as you increase the number of windings, the capacitance between each winding began to intrude. But the advantage of having multiple windings on the BH curve, that is the current flux curve, was in favor of more windings. Of course, more windings means more complicated, more expensive, and so on. So in addition to having to be a pretty big amplifier, big transformer, a lot of iron, the number of windings made a difference. The second thing that Williamson talked about is the need for some kind of phase splitter. If you take a single-ended signal, like the output of the tone or the crystal of a record player, for example, you can amplify it single-ended for a while, but eventually you have to convert it. If you're going to use push-pull outputs, you have to convert that single-ended into an in-phase and out-of-phase signal to drive those two output tubes. That's the purpose of this stage, and we'll look at a whole series of articles on this issue, that is, the issue of designing phase splitters. And then finally, one of the things that Williamson did that was really to revolutionize hi-fi amplifiers was the use of feedback. Now you'll notice that there is a signal that comes from here, runs around here and connects to this resistor. That is the feedback in this amplifier, and it's called global feedback. I did a couple of videos on global and local feedback that you might want to look at if you're not familiar with the basics of feedback. So the three things that Williamson introduces in this article that I consider important, or this pair of articles, is transformers, phase inverters, and feedback. The next article is really a follow-on from the first video on these magazine articles, where I talked a fair amount about the question of what is good reproduction, or in other words, how can you relate what you measure in the lab to what you actually hear in your living room. This is a pretty nice summary of a discussion that took place in 1948 by the British Sound Recording Association. And so I recommend it to you because they talk about some of the factors in a nice summary, one single page. And this appeared in the January 48 edition of Wireless World. Before I get too much further in this video, I do want to mention, for those of you that haven't found it already, all of the magazines I'm going to be talking about in this video, as well as the ones in the last video, and if I do any in the future, those as well, are taken from this website. It's called AmericanRadioHistory.com. You see it all run together there. And this is, at least to me, the best collection of articles on, it's not just radio, it's electronics, it's repair, it's television, it's everything from the recording industry to the broadcasting industry. They've got just about every publication that I'm aware of in this area. And the nice thing is they're all downloadable, they're in PDF, some of them are searchable. So you can actually do searches for words inside PDF articles. It's a wonderful resource. So use and support this site, please. I think it's a real valuable resource. The next article is from the January 1948 Wireless World as well. In other words, the same month as the article on reproduction we just saw. And it's an article, once again by Baxendall, called High Quality Amplifier Design. I consider this to be almost as important as the Williamson article because He begins in the first paragraph saying, in the April and May issues of Wireless World, a design for an audio amplifier was described using triodes in all stages and giving an output of about 14 watts. The nonlinear distortion and hum being reduced to a very fine level by the application of about 20 dB of negative feedback over all 4 stages. That's about as good a summary of the Williamson amplifier as I have ever seen. And then he goes on to discuss, well, wouldn't it be nice if we could use pentodes instead of triodes, because pentodes are so much more efficient. The problem that pentodes have is the kink in the transfer characteristic. The kink is due to the absorption of electrons by the screen grid, and later attempts were made to produce triodes or pentodes without that kink. They were often had the designation KT. So, for example, if you see a KT88, the KT stands for kinkless tetrode. But at the time that Baxandall published this article, those were not available. One of the suggestions that Baxandall makes in this article is the use of a separate winding on the output of the output transformer to provide the feedback. Later, this was used by many manufacturers, including Macintosh and Scott and some others that I'm aware of, in this form or in other forms. And basically the idea is using the output winding that's really designed to drive the load because the load itself, a loudspeaker, is a variable reactance, it causes the feedback signal to have a built-in nonlinearity due to the reactance change of the loudspeaker with frequency. So he proposed using a separate winding. It's a really good idea. It helps to eliminate a source of distortion in the feedback loop. And this, as far as I can tell, is the first mention of using that kind of a circuit. Baxandall then proposed his own circuit design for what he calls a high-quality amplifier. And once again, this is a slightly different way. This uses 6L6s in the output, which are simply a low-power pentode. By low power, I mean it was high power as radios go, but as transmitters and so on go, it was a relatively low-power output tube used in a lot of radios of the day. You'll notice what he's doing is he's using the pentode, but he's tying the screen grid through a resistor to the plate supply. Now, one reason that he's doing that is to make the pentode behave a little bit like a triode. In other words, try to eliminate some of the kink in the characteristic curve. I won't go too much into that in this article because it's probably better if you read Baxandall's description. He's very good at describing these things. Here is the third harmonic distortion that Baxandall measured for the amplifier, the circuit of which you just saw. The output power is across the bottom, and this is 12 watts. And then percentage distortion, now this is third harmonic distortion, is up this side. This is 0.1% and 0.2%. So as you can see, he was able to get quite good distortion for the day. This was one of the lowest distortion amplifiers. Now, he does use 36 dB of feedback, and the use of feedback, particularly more than 20 or 30 dB of feedback, became problematic for reasons of stability and transient response that we aren't going to get into here. But if you want a little bit of coverage of that, go back and look at the videos I did on hi-fi tube amps and also on measuring hi-fi tube amps. You'll find that one of the reasons that square wave analysis was introduced was because a feedback amplifier with more than about 30 dB of feedback often has poor transient response, overshoot and ringing, things of that sort. This next series of articles, all by W.T. Cocking, that appeared in Wireless World beginning in January of 48, and the final installment was in May of 48, talked about push-pull input circuits. And what he's really talking about here is converting single-ended to phase splitter design to drive push-pull stages. So what he's really saying is how or what are the different ways and what are the advantages and disadvantages of those ways to produce a push-pull signal from a single-ended signal. In the first part, part one, the author talks about general principles and the use of transformers to provide phase splitting. I'll show you the picture that he shows here of a single-ended and a push-pull with a push-pull output, and so he treats the transformer here as just a black box. But as he points out in that first part, transformers leave a lot to be desired. They have a lot of bad characteristics, particularly when you look at their characteristics across a wide band and across low and high power, transients, etc. So in part two, he talks about cathode follower phase splitters. This is where you put approximately the same size resistor in the plate and in the cathode. You drive the tube at the grid, and instead of having a grounded cathode, you have a cathode from which you're taking one of the outputs of the dual phase signal. One of the problems of these is that you just can't find a tube that has the same plate current as cathode current. The reason is there are other currents flowing out of the tube from the cathode that don't go to the plate. And so no matter how you design a cathode follower phase splitter, there will always be some loss of current, and therefore you wind up doing things like making the cathode resistor a little bigger than the plate resistor. But then that brings in issues of frequency response and capacitance and so on. Good article if you're designing or just want to analyze a cathode follower phase splitter. I can't recommend a better article than this one. In the third part, the author discusses phase reversers. Now, a phase reverser, this is essentially the same kind of circuit that Williamson used in his amplifier. It's the use of two tubes where you connect the cathodes together with a common resistor. That is, the cathodes are connected to each other and then they share a common resistor to ground. You drive one tube and ground the grid of the other tube. In this case, he has it connected to a voltage divider off of the this line, which is also coupling the output. So the idea of this phase reverser is to make up for some of the problems that cathode follower circuits have. Once again, if you're working with or analyzing this kind of a phase inverter, this is probably one of the best articles I know of on that. By the way, while I'm talking about this, I do want to put in a plug for a book called Valve Amplifiers. It's written by a guy named Morgan Jones, and it's in its fourth edition, or at least that's the edition that I have. I used to have the third edition, but I looked for it several months ago and couldn't find it, so it may be in a box up in the attic. But at any rate, I ordered this fourth edition at that time, about 6 months ago. One of the nice things is this is a modern book. It contains a lot of what I'm talking about here, and it contains it in a nice, concise collection, if you want to call a book this thick concise. But it's a really nice overview of many of these same topics, but all collected together in one book. Moving on to part 4. the author discusses what he calls the anode follower. Now, this circuit actually dates back to the 1930 and was often called the paraphase amplifier. It sometimes is also called the seesaw circuit, and it's shown over here. And a lot of these were used in hi-fi amps of the day. In fact, the Williamson design is a little bit of a mix between the cathode follower and the anode follower. What it does is, instead of having 3 tubes, it allows you to drive one tube and use a second tube at the same time to produce a phase inversion, so that you get 180-degree phase reversal here with respect to here. The final, part 5 of this series, is on cathode coupled stages. And here is the circuit that he talks about. And in this particular thing, or this particular diagram, he's eliminated the bias networks. One of the reasons that it is important to talk about the bias network, though, is this is essentially a direct coupled phase inverter. And what that means is that you have to bias one tube differently from the other tube to account for the gain, the DC gain of any preceding stages. So the discussion on this is useful, but frankly, there weren't very many of these used. So if you're looking for an article to skip, you might want to skip part 5 of this. It's of academic interest mainly, and not really of much practical interest, at least with regard to the amplifier designs that were used in the 50s and 60s. The final article from Wireless World that I'm going to talk about is a return to the question of how much does distortion matter, and if so, how much. This appeared in the March 1948 edition of Wireless World. So in other words, this is right in the middle of the series of articles we just talked about. And as you see in the subtitle, it talks about the extent of its, that is, distortion's effect on reproduced speech and music. It's an interesting article. It raises more questions than it answers, but nonetheless, it is a good survey of what sorts of questions do you need to ask when you're trying to decide, well, if I want to put money into an amplifier and reduce the distortion or increase the power or raise the frequency response, where is my money best spent? And while that's not specifically what the author is talking about here, the questions that are asked in here and some of the proposed answers go to that matter. That is, where is the best place to put your money? In this article, we're changing publications. This is Audio Engineering, the July 1951 edition, and I saved it till now because of the article I just talked about, Does Distortion Matter? Because this is a way of measuring and analyzing intermodulation. Now, up until this article, most people focused on harmonic distortion, or in some cases, total harmonic distortion. In other words, the harmonics of the input signal. So if you had a 1 kilohertz signal, they were focused on the 2 kilohertz, 3 kilohertz, 4 kilohertz components. Music doesn't work that way. Nobody plays one note continuously throughout an entire piece. There are multiple instruments, there are multiple strings on a given instrument, they're all being played at once, so what you have is a mix of frequencies. So, suppose that you have a 1 kilohertz and a 1.5 kilohertz. That means you not only have a 2 kilohertz from the 1, You also have a 3 kilohertz from the 1. You also have a 3 kilohertz from the 1.5. And you have a 2.5 kilohertz from the mixing of the 1 and the 1.5, and so on. So the number of possibilities when you have two frequencies gets multiplied, actually gets squared. Then if you add a third frequency, it gets cubed, and so on. So what you wind up with is a real mishmash of the interaction between the various frequencies. So you have harmonic distortion, 1, 2, 3, 4, 5, and you have intermodulation, 1 with 1.5, 1 with 2 fed back from the output, 1.5 and 1, or 2.5 with 2, and so on. Very good article. However, the method that is talked about in here is somewhat out of date, and there are better ways of measuring intermodulation these days. But it's a really good overview of the way that intermodulation distortion was measured in the day, and I frankly think it's a good article to start with if you're trying to understand even modern intermodulation analysis. And finally, we come to the last article I'm going to talk about in this video. This is the Hafler and Keros article on an ultralinear amplifier. And the ultralinear was an attempt to figure out how you can use pentodes but get the linearity of triodes. Now, that was never completely achieved, even with kinkless tetrodes and beam power tubes and other things, but with feedback you can get awfully close. Here is the schematic of the amplifier that was proposed in this article, which, by the way, appeared in the November 1951 edition of Audio Engineering magazine. Notice the difference in the output transformer. Now, you still have multiple taps for speakers on the output, but the primary also has a tap for the screen grid. So for the first time, in addition to the plate being connected to one end of the primary and the secondary being essentially grounded, there is an intermediate tap that feeds the screen grid. And one of the questions that they ask in this article is, where should that tap be to produce the best linearity? Now, obviously, if you connect this all the way up to the top here, in other words, you put this tap at the top, it's the same as the plate, and now the pentode becomes a triode. If you remove this tap and connect to the center tap the screen grid, or actually you would have to connect it to a voltage to provide screen voltage, but nonetheless grounded with respect to an AC signal, then you're operating this in a pure pentode mode. So by moving this tap up and down, what you are basically doing is moving from a triode to a pentode. And the question that is discussed in this article, and frankly became a topic of discussion, argument, maybe even bar fights over the years, was, does this really do as much good as the authors think it does? Let me show you a chart that I found helpful. What this chart tries to do is to show the characteristic curves of a triode, this bottom black line, a pentode, this top line. Notice a triode isn't linear, neither is a tetrode. The idea, and the authors here have idealized this, the idea is to have the ultralinear circuit run right down the middle. That is, use some of the elements of the tetrode and some of the triode, and since the tetrode tends to curve down as it goes higher and the triode tends to curve up as it goes higher, the idea is, well, we'll kind of balance these out and we'll get a position in the middle. Well, you can tell just by looking at this chart that it's idealized. if you draw a dotted line that basically splits the difference between this line and this line, you'll find that it goes up like this, and then comes down, and then goes through this point, and then changes again, and so on. So there's no such thing as a completely linear amplifier. An ultralinear is better than a tetrode. Many people consider it better than a triode because it's much more efficient. But the reality is that a triode produces sound that most people find better if you're willing to pay the cost of bigger tubes, bigger transformers to make up for the low efficiency of triode amplifiers. So I'll leave it to you to decide whether you like the sound of an ultralinear amplifier better than a triode amplifier. It is a question of how much money you're willing to spend. But for people who have a seemingly inexhaustible supply of cash, you'll find they generally buy triode amplifiers and just put up with the low efficiency by basically making the amplifier more massive. Well, once again, I hope this has been of some use. I'm going to put the articles, the list of articles, back up here for those who might want to look at or pause the video at this point so they can copy down the various editions that we're talking about. The first one from Electronics World, then a group from Wireless World, and finally the last two from Audio Engineering. Hope you enjoy these. I'm going to go on reading, but how long it'll be before I collect enough articles to do another is, well, yet to be determined. But in the meantime, have a nice day.